I'm Aymeric Dieuleveut. I'm a professor of statistics and machine learning at École polytechnique in the applied math department. I'm also one of the scientific co-directors of the High Paris project, and I'm very happy to be one of the speakers at the High Paris Summer School 2025. Conformal prediction refers to a set of tools used in machine learning to quantify the uncertainty of machine learning predictions. Machine learning methods have become more prevalent and are used to make predictions in various aspects of our lives. However, those predictions often come from black box algorithms for which we do not really understand how the algorithm predicts. In order to gain trust in those models, one solution is to go beyond point prediction. Instead of making a single prediction, we try to predict a set of values for which we can guarantee that the true output, the truth, is actually contained in the set of values that are output. This is the goal of conformal prediction. There are several key trade-offs in conformal prediction, many that we have actually reviewed during the tutorial. One of the first, most fundamental trade-off is the computational versus statistical trade-off. Among all possible conformal prediction methods, some have better statistical dependency, are efficient with very few data, and some require more computational power. We reviewed the two extremes, including split conformal prediction methods until full conformal prediction methods. Another very important aspect is the strength of the guarantees we can get. The guarantees are typically what we call marginal validity. They are true on average over many sources of randomness. Building methods enables us to go closer to some kind of conditional validity, meaning that the guarantee we get is more specific conditionally to some source of randomness. This is also a very important trade-off that we detailed during the tutorial. Conformal prediction has been used in many domains of applications. For example, some of the results that I presented in the tutorial are based on Margot Zafran's PhD. Margot was doing a CIFRE PhD with EDF, the French electricity group. We leverage conformal prediction in order to quantify the uncertainty of price prediction for electricity, which is a crucial aspect of electricity planning. Privacy, robustness, decentralization, and conformal predictions are all connected to trustworthiness in machine learning models. To some extent, those techniques are a bit different. In robustness, we try to consider the impact of adversaries. In decentralization, we try to tackle the fact that models could be learned at the scale of networks of agents. In privacy, we want to ensure the privacy of the data. In conformal prediction, it's all about quantifying the uncertainty of the model. Despite those differences, they are all connected in that goal of making machine learning techniques more suitable for the public. There is another interesting aspect, is that on the methodologic parts, they are connected in terms of which tools they use. Many of the things we do are connected to optimization in machine learning, and we leverage similar tools for both conformal prediction and decentralized learning. One common misconception is that people believe that conformal prediction is opposed to other techniques like Bayesian learning or probabilistic prediction. In fact, one of the key strengths of conformal prediction is that it can build on top of almost any methods that would have been trained before by practitioners. We can build on point predictors or quantile regressors or even probabilistic predictors. That enables us to benefit from all the knowledge and all the expertise accumulated over many years. And in many application domains, it is actually key because the people do not want to retrain a model from scratch just to add uncertainty. This makes conformal prediction actually very useful. It can be used using off-the-shelf models that have been developed in the past. And at the same time, the techniques, while remaining very simple, can be applied to virtually any domain.